Hi, today we're going to be doing functions from Additional Mathematics Chapter 2. So to start off, we have to be able to differentiate between a relation and a function. So a relation is any set of points which connect two variables, for example x and y. So the examples include y equals 2x plus 3 or y squared equals 4x minus 4. And a function is a little different to a relation. A function is a relation in which no two different ordered pair have the same x coordinate. So we'll learn more about it in the next few slides. So basically what I'm trying to say is that every function is a relation, but every relation is not a function. And so examples include y equals 2x plus 3 or y equals 4x squared plus 3x minus 4. The next part is mapping. So as you can see the diagram, this is called mapping. This would be the x coordinate values and this would be the y coordinate values for all of these. And a relation is called a function if for one value of x there is only one value of y. So here this would be a function because one value of x only maps to one value of y. You can check it for every single one, even for this one. But then for this one, if you look, one value of x gives you two different values of y. So this would not be considered as a function, as I've stated here. Even over here, minus 9, this is the x coordinate values, remember, and this is y. So one value of y, one value of x is being mapped to two different values of y. So that's why this is not a function. So why don't you try these problems on your own? Check if, I will let you know the answers when you have finished. So you have to check whether these are functions or not. So you could pause the video. So I will tell the answers now. This is a function because one value of x maps to only one value of y if you check for all of them. And then this is a very special kind of function which we will do later. Only one value of x is being mapped to only one value of y. So this is a function. How about this? No. One value of x is being mapped to multiple values of y. So obviously this is not. So even this is true for this one because 1 is being mapped to minus 0 and 15. So this would not be a function. And this one, this would be a function because one value of x correlates to one value of y. Okay, the next part is type of relations or also functions. The first one is called as a one-to-one. This would be a function because one value of x maps to only one value of y. I mentioned previously that this was a special type of function because of this. It's called as a one-to-one function. The second one is a many-to-one, meaning many values of x can map to a single value of y. This would be a function because because it's a many-to-one, meaning that two different values of x map to one value of y. Here we could take y equals x squared, meaning if you put x as 1 or minus 1, the answer would be the same. So this would be a many-to-one function. The last example, it's one-to-many. This would not be a function because one value of x maps to two different values of y. Since we mentioned over here, it does not fit this criteria, right? So that's why that would not be a function. So one-to-one, many-to-one are functions, and one-to-many and many-to-many are not functions. They would be relations. But the thing is, many-to-many is not in like the syllabus It basically states that like many values of x map to many values of y. That's basically it, but it's not part of the syllabus, so I'm not going to go deep. But we can, for one to many, the examples would be y equals plus or minus square root of x. Even if you put the value as 1, x as 1, you'll get two values of y, which is plus 1 and minus 1. Therefore, it would be called as a relation and not a function. Just remember, these two are functions, this one is not. Okay, to check whether a relation is a function, we would use something called as the vertical line test. A vertical line test is used to see if a relation is a function or not. So that's, yeah. So we'll have to draw a vertical line over the graph that you have. And when we draw a vertical line, if the graph cuts the line at two or more points, it's not a function. So if you draw a vertical line anywhere here, this is it cuts at 1 point, here 1 point, here 1, here 1, 1 and 1. Therefore it would be a function. But over here we have drawn that vertical line, but it cuts the point at two different points, so that would not be a function. The explanation is pretty simple, that a single value of x maps to two different values of y. As we saw, this would be considered as a one-to-many, meaning one value of x maps to two different values of y in this case. It can map to like many values of y. And hence this is not a function and this is a function. So you can try these problems on your own, these 5 problems, and I'll tell the answers. You can pause the video because I'm going to tell the answers right now. Okay, the first one is not a function. It's kind of easy. Just draw the vertical line. It cuts at 1 and 2. And this is a function because it will only cut at 1 point. This one, it is not, because if you draw a line here, it would cut 1 and 1. So that would be 1 plus 1, 2. This one, definitely not, because it does not cut at 2 or more points. This one was definitely slightly tricky because these points I haven't really explained them. So basically an open circle means that the point is not included. A closed circle means that it is included. And yeah, and the arrow means that it will continue in that direction. So this would not be a function actually, because if you draw a vertical line here, meaning that this point and this point are included, so the vertical line is cut twice, one here and one here. But here it's being only cut once, so it's here. So if this part of the graph wasn't there, this would have been a function. Okay, the next one is a horizontal line test. This is somewhat similar to the vertical line test, but here we are checking if a function is a one-to-one function or not. So what we'll have to do is very similar to the vertical line test, draw horizontal lines instead, and we'll have to see if the line is being cut twice or more than that. So here it's only being cut once, so it would be a one-to-one. Whereas over here, if we draw a line here, it's being cut thrice, 1, 2, 3. Even over here, it would be cut twice. Therefore, it's not a one-to-one function, but rather it's just a many-to-one. One-to-many function. Sorry, many-to-one function. Okay, you could try these problems on your own. Okay, I'll tell the answers now. If you haven't done it, just pause it and do it right now. So here, if we draw a horizontal line here, every single point is on that horizontal line. So therefore, it's not a one-to-one function, but it is a function because it passes the vertical line test. And this graph, it would definitely be a one-to-one function because it's being cut only once if we draw the horizontal line here. and also it's also a function because it passes the vertical line test. And this one, it's not a one-to-one function because if we draw a horizontal line here, it's being cut thrice here, twice here, and twice here. This point, it's not. I mean, it is a one-to-one function because if we draw the horizontal line, it's being only cut once. And this one, no, it's not a one-to-one function. Okay, the next part is function notation. It's like there's really nothing to explain here. It's just that you'll have to replace y with f of x. So that's all. Like you just write the value of x within here. And if you want to replace with 2, like x with 2, you'll have to write f of x equals 3 into 2 plus 3, which is 6 plus 3, that is 9. And that's all there is to this. The next topic is domain and range. Domain, it is the set of values that the variable x can take such that the function is defined. This is very important, such that the function is defined. For instance, if we take 1 by x, we cannot take x as 0 because then it would be undefined. So therefore the domain is everything, all real values except 0. Like for example, I have given here y equals x plus 3. The domain is for all real values. You've probably learned this notation in sets. So x belongs to all real values. And similarly, range, it's the set of values that the variable y can take such that the function is defined. So for example, y equals square root of x plus 3. The range is greater than or equal to 0. We know that square root of something cannot be negative. Therefore, the range is y greater than or equal to 0. Okay, I think the book has explained really well like how to find the domain and function. Domain and range. So therefore, I'll be looking at these examples from the book. So square root of x minus 5 is defined when this value is greater than or equal to 0. Else if it's less than 0, it's not defined because we don't know the square root of a negative number yet. So we'll have to equate that. If you find anything like this within square root, then you'll have to do this procedure. So x minus 5 is greater than or equal to 0. Therefore, x is greater than or equal to 5. And this is how you write the notation. In brackets, x dot x greater than or equal to 5. Or you could just sometimes write x is greater than or equal to 5. Okay, similarly, a square root cannot be negative. And hence the range is y is greater than or equal to 0. The next example is 1 divided by x minus 5. It's defined when this is not equal to 0. It could take any value of x except x equals 5, because when x equals 5, this would be 1 divided by 0, which is, well, undefined. So the domain is everything except x equals 5. So it's true for all real values except 5. And like they said, no matter how large or small x is, y equals f of x is never 0 because, well, like it's very obvious, 1 divided by something just cannot be 0. Like if you even equate it to 0, meaning 1 equals 0, which does not make sense. So therefore the range is everything or for all real values of y except y equals 0. That's what it says. And this is the graph. As you can see, this is an asymptote. Basically this line is approached by this but never touches this line. It's like it's infinitely close to this line, but the graph never cuts it or even touches it. Okay, the next one is a combination of these two. So it is defined when x minus 5 is greater than or equal to 0, because less than 0, first of all, the root part wouldn't work, and if it's 0, the 1 divided by 0 would not make sense, hence it's not defined. Therefore, they have stated that this is defined when x minus 5 is greater than 0, meaning x is greater than 5. So therefore, the domain is this. And as they have stated, is always positive and never 0. Like in this case, we said that it's everything except 0, right? But here this cannot be negative because the square root part cannot be negative. So therefore, it's positive. And this cannot be 0 like I previously mentioned. And this is the graph. Okay, the next part is the modulus function, which is also known as the absolute value function. So I have just stated a few key points here. If f of x is the modulus of x, and that will equal x if x is greater than 0, minus x if x is less than 0, and 0 if x is 0. So this might be confusing, but just remove the sign on the value, meaning if it's negative, it will become positive. If it's positive, it will remain positive. So I've given a few examples here. So modulus of 4 equals 4, because I've given the explanation. If you look at this, I've drawn it parallel to this. This is the reasoning, since 4 is greater than 0. And modulus of minus 9 is 9, because 9 is less than 0. And modulus of 0 will be 0. It's very simple. And there are two methods of solving the equations. The book, I think, has mentioned only one of them, which is this, but you could also use this. So let's take this example. Modulus of 5x plus 7 equals 3. So for the first method, you'll have to remove the modulus symbol and put plus or minus for the whole thing that is after the equation symbol. So we write 5x plus 7 equals plus or minus 3, and implies that f of 5x plus 7 equals 3 implies 5x. By transposing this term, we can make it equal to minus 4, and then dividing both sides by 5, we get x equals minus 4 by 5. Or we could do this again, but put a minus symbol in front of this. So 5x plus 7 would equal minus 3, and then 5x would equal minus 10, and divided by 5 would be minus 2. So these two are the answers. And then there is another method, the one where you can square both sides. So 5x squared plus 7 whole squared equals 3 squared. And yeah, you just expand what's inside the brackets and equate it, and use the quadratic formula, or like splitting the middle term, and find the roots. So either way, you'll get the same answers, but I prefer this method because this is very lengthy and it's kind of time consuming. Plus, you'll have to find out the quadratic equation, and then you'll have to solve it. So it will take more time. Therefore, I prefer this method. But if you have no problem, you can do this also. Why don't you try these problems on your own, and I'll reveal the answers after you've done. So just pause the video right now and solve these, and I'll reveal the answers. Okay, these are the answers. I'll just solve one of them right now. Okay, I'll just probably solve these two. So the first equation was modulus of 3x minus 2 equals 1, I think. Yeah. This implies that 3x minus 2 equals plus or minus 1. So you can write case 1, 3x minus 2 equals 1 implies 3x equals, transposing minus 2 to this side would become 3, implies that x equals 1. And then case 2 would be 3x minus 2 equals minus 1 implies 3x equals 1, implies x equals 1 by 3. Therefore, x equals 1 or x equals 1 divided by 3. The next one is this one. Yeah, we'll just solve this. This may seem complicated, but you'll have to do the same procedure. Just think of this as a constant. So if you had 1 here, you'd just do plus or minus, right? So you'll do the same thing here. 3x minus 1 equals plus or minus the whole thing. This whole thing. Case 1. 3x minus 1 equals x plus 2. Transposing it to this side would give you 2x equals 3, and then x equals 3 divided by 2. And then case 2 would be 3x minus 1 equals minus x minus 2. Always remember the multiplying rule. So this would be 4x equals minus 1 implies x equals minus 1 by 4. We got x equals minus 1 by 4 and x equals 3 by 2, which is the answer. Solve these two the same way. And then we move on to the graph of a modulus function. Basically, it is the reflection of the part of the graph which is below the x-axis, basically which has a negative y value, and you'll have to reflect it over the x-axis or take I hope you've learned the reflection thing. So the example, the book has given it really well. So here, this part was below the y-axis, hence there's just imagine this is probably like a mirror or something, so it will form the image exactly like that side. Therefore, this is the graph of the modulus of f of x. So yeah, that's basically it. If you want, you could read this. It's very informative. The next part is called as composite functions. It's basically combining two functions like f of x and g of x. So this is how you read it, f of g of x. This is also equal to f of g of x. Don't confuse this as f of x into g of x. It's f of g of x. You could also write it as this, or even this, but I'd prefer using this because it's more clear. This is a little more complex. I'll try to explain it in a simple way. The book somehow did this more complicatedly. So I will just take this example and I'll explain it. So over here, they said that f of x equals x to the power 4 and g of x equals 2x plus 3. Okay. F of x equals x to the power 4, g of x equals 2x plus 3, I presume. Yeah. So if you want to find f of g of x, what we'll have to do is write this whole thing. Oh yeah, by the way, just remember that don't ever write this because it means something completely different. So we'll learn that maybe like in the last chapter. So write this the g of x, the whole thing. So 2x plus 3. Like I said in the function notation, you replace this value with this, meaning if this was f of 2, you write 2 into 2 plus 3. So whatever's inside the brackets, you substitute the value over here with x. So that would be 4 plus 3. And in a very similar manner, you'd just consider this as capital X. So if you write f of x, you just write f of x. Let's just say let 2x plus 3 equals, actually let's take y because it's very distinct from x. Yeah. Now what we do is we'll write f of y. So you just replace this value, right? So that would be y to the power of 4. Now let's substitute y with what we equated it. So that would be 2x plus 3 to the power of 4. So that's it. Okay, now g of x, f of g of x is not equal to g of f of x. Okay. So this is the answer for that. So we'll find g of f of x. So f of x was x to the power of 4 and g of x was 2x plus 3. Let's find g of f of x. This would be g of this value, which is x to the power of 4. For now, for your convenience, I will just write let y equals x to the power of 4. But then when you're doing like the past papers or something, just ignore this step and just write it directly. So this would be g of y, and what would be g of y? It would be 2y plus 3. Let's substitute this back into the equation. 2 into x to the power of 4 plus 3. Yeah. So we got this answer, which is very different from this. So therefore, f of g of x is not equivalent to g of f of x. Okay, the next important thing is this thing. You may think of this, you may think that it is f of x whole squared, which is not the case. This is basically f of x. It's the composite function of f of x. So we would write this as f of x. We could find this in this case because we will take f of x equals x to the power of 4. So this would be f to the power of 4, and this would be to the power of 4, which is 16 to the power of 16. And yeah, let's take another example. Let's just write g of x equals, let's take something very complicated, square root, not that complicated also. Let's just write tan inverse of x. So g of x would be g of tan inverse of x, and let g of x, so g of tan inverse of x would be tan inverse of x. Yeah, and let's just take h of x equals maybe x to the power of 4 plus 3x squared plus maybe 2 square root of x plus 3. So this would be h of, we write this whole equation down. Okay, this is going to be a very long one. Plus 3. Yeah, it's quite simple. And also if you get this, it basically means that it's h of x. Yeah, that's quite simple. Okay, now you can try these problems. You can pause the video. So I'll now reveal the answers. This is the answers, and I'll solve a few problems also. So I will just take a photo of this and paste it there. So the first one's really simple. I'm not going to solve it because all you'll have to do is replace x with 0. So you just get b equals d. and replace with 1, and you'll just get it. It's very simple. Let's go with b. So f of x equals 2x plus 3, and g of x equals ax plus b, and they have given this one, they have given this. So let's do it. You know what, I'll just rewrite this. So it would be g of x equals ax plus b, and now we have to do f of g of x, and this equals x. Okay, so we have f of g of x is ax plus b, and this equals x. And now we'll do green. So this would be 2 into ax plus b plus 3 equals x. So now we'll just have to solve this. 2ax plus 2b plus 3 equals x. And we can group together the like terms. What we can write x as it's 1 into x plus 0. So this, I think it's called the method of comparison or something. So what we'll have to do is we'll have to equate 2a equals 1, because these two variables are the same, so we could do that. So a equals 1 by 2, and we have to equate this to 0. So 2b plus 3 equals 0 implies 2b equals minus 3 implies b equals minus 3 by 2. And yeah, that's the answer. And if is the result in b true if g of f of x equals x? Okay, so what was g of f of x? F of x equals f of x equals 2x plus 3, g of x equals ax plus b. And let's try. Yeah, let's just solve this. No, it was the other way around, g of f of x. So this would be 2x, I think. Yeah, 2x. So g of f of x equals x implies g of 2x plus 3 equals x, implies that a into 2x plus 3 equals plus b equals x plus 2ax plus 3a plus b equals x plus 0. Let's just write that. So implies that 2x equals 1 by 2x equals 1, implies a equals 1 divided by 2, and 3a plus b equals 0. We can substitute this value here. It would be 3 divided by 2 plus b equals 0 plus b equals minus 3 by 2. We got the same answers, so it is true for all x. Let's solve the next problem. they want us to find f of g of x. This equals f of g of x equals x squared equals square root of 1 minus x squared. So that's the value of this. And the domain and range of, they want us to find this. So we have done the domain and range. So we know that 1 minus x squared must be greater than or equal to 0, because square root of a negative number is not defined. Okay, so basically this is negative real numbers. Could also write it as this. So square root of a negative number is not possible. So this is what we have got to do. 1 is greater than or equal to x squared implies that minus 1 is less than or equal to x is less than or equal to 1. So that's the domain. And range is basically f of g of x is greater than or equal to 0. Yeah, that's quite simple. So yeah, moving on. So inverse functions. The book has made it really complex when there is no need to, and I think they haven't thought how to solve these equations, inverse functions, or how to do it. So this is, I've tried to put it in the most simplest way possible. So yeah, these 3 points are one of the most important things in inverse functions. Okay, the first point says that the inverse of a function is a function obtained by reflecting the graph of the original function across the line y equals x. I think that's very clear and straightforward. I'll just show you the graph. This is the graph. So you basically draw a line y equals x, and this is the original graph, meaning you'll have to reflect it over this line. So therefore you get this line, this graph. So that is the inverse. And the next point, property, domain of f of x becomes the range of f inverse of x. Oh yeah, this is how you denote an inverse function. It's f of this. By the way, this is not equal to f dash of x. This is basically dy by dx, which is calculus. So these two are very different. This is a dash, whereas this is a minus 1 on top of f. So f inverse of x. Yeah, this is how you denote it. And yeah, so domain of f of x becomes the range of f inverse of x. You'll soon know why. And also the vice versa holds true, meaning the range of f of x becomes the domain of f inverse of x. And for a function to have an inverse, it must be a one-to-one function. Even if a function is not a one-to-one, we can restrict the domain so that for that particular domain, the function is a one-to-one for that region itself, for that region only. So yeah, I think you'll learn that later. Like obviously it's not really mentioned in the book, but it's always there in the past papers. So yeah, just remember that you can restrict the domain to make a function one-to-one. Yeah, I'll show you how you'll restrict the domain. So we draw this on the Cartesian plane. We'll draw y equals x squared, which is a quadratic equation. And we'll draw a parabola which passes through the origin. So as we know, this is a function because it passes the vertical line test. But then we know that it's not a one-to-one function because it does not pass the horizontal line test, because it cuts the graph at more than one point. So hence we know that it is not a one-to-one function. So I'll show you how to restrict the domain. Okay, what you can do is either you can consider from this to this or this to this. Hence, it would be considered as a one-to-one function because it does pass. If we delete this portion, and this would be considered as a one-to-one function. So that's how you restrict the domain. You can state the value. So f of x, y equals x squared for x greater than or equal to 0. This is how you restrict the domain. So for this value, this is a one-to-one function. For this range, for this domain, this function is a one-to-one. So therefore, that's how you restrict the domain. Yeah. Okay, so this is the graph that I showed you. In the book, they haven't really mentioned how to solve these problems, but I've encountered these type of problems maybe every 2 papers. So I'll just explain it. So step 1, you'll have to swap x and y and make y the subject of the equation, and you'll have to replace y with f of x. So first I'll show a very simple example, which is I'll just take y equals x minus 3. I think this is the most simple you can go, and replacing y and x, we get x equals y minus 3, and we'll have to make this the subject of the equation. So by transposing this side, we'll get we'll make y as the subject of the equation. So this. So therefore f inverse of x equals x plus 3. So this is how you find the inverse. And let's try a little more complex. So y equals x plus 1 divided by 2x minus 3. Oh yeah, just try to solve it first, and then you can pause the video now. I'll just do it now. You can solve it, and then once you have done, you can follow. So y equals x plus 1 divided by 2x minus 3. Now swap these two variables. So that would mean x equals y plus 1 divided by 2y minus 3. Let's multiply both sides by 2x minus 3. So that would be x into 2y minus 3 equals to y plus 1. Let's just multiply this. 2x y minus 3x equals y plus 1. Let's transpose it this side. So that would be 2xy minus y equals 3x plus 1. Let's take y as a common factor. So 2x minus 1 equals 3x plus 1, implies y equals 3x plus 1 divided by 2x minus 1. Therefore, f inverse of x equals 3x plus 1 divided by 2x minus 1. So this is the answer. Yeah. I'll just solve the other one also. The other one is very similar. I thought of not solving it, but then I'll have to give the answer, so I'll have to work it out. X plus 1 divided by 2x minus 5. So 2x minus 5. Oh, I forgot to swap the variables. That is x equals y plus 1 divided by 2y minus 5, implies that 2y minus 5 into x equals y plus 1, 2xy minus 5x equals y plus 1, 2xy minus y equals 5x plus 1 implies y into 2x minus 1 equals 5x plus 1 implies y equals 5x plus 1 divided by 2x minus 1. Therefore, f inverse of x this value. Yeah, that's it. That's all you need to know for functions. Yeah, bye.